Welcome to Physics Inside Out.
Today, Physics Inside Out has brought to you the experiment to find the coefficient of viscosity of a liquid by falling sphere method. For your understanding, we have categorized the experiment into the various sections, in which first is introduction to the experiment, then complete description of apparatus, and after that, we shall perform the experiment, note observations and calculations, and finally interpret the results. First is the introduction to the experiment. The experiment to determine the coefficient of viscosity of liquid using the falling sphere method basically relies on two concepts. First is the Stokes law and second is terminal velocity. Stokes law describes the drag force experienced by a spherical object moving through a viscous fluid, whereas viscosity is the measure of fluid's resistance to flow or deformation. It determines how thick or sticky the fluid is. The falling sphere method utilizes the motion of a sphere descending through a liquid under the influence of gravity, which is the downward force acting on the sphere due to its mass. And this motion due to gravity is actually resisted by the viscous drag force of the liquid. This viscous drag force is that force opposing the sphere's motion through the liquid due to the liquid's viscosity. And this method relies on achieving the terminal velocity, and this terminal velocity is achieved when the upward forces, upthrust and viscous drag balance the downward gravitational force. It means the constant velocity is achieved by the sphere when all the forces, that gravity force is equal to upthrust force plus the drag force. This upthrust force is the that upward force exerted by the liquid on the sphere due to its displaced volume. And when the upward forces and downward forces balance each other, the equilibrium condition is achieved. And this equilibrium condition allows us to calculate the liquid's viscosity by measuring the sphere's diameter, fall time and correcting it for boundary effects as eta equal to rho b minus rho l into g d1 square t divided by 18L into 1 plus 2.4 d1 over d2 into 1 plus 1.6 d1 over h. Here in this relation, rho b is the density of material of ball, rho l is the density of liquid used, g is acceleration due to gravity, and this d1 is diameter of sphere, t is the time the ball takes to fall the distance l, this l is the distance the ball falls at uniform speed, d1 is again the diameter of sphere, d2 is the inner diameter of measuring cylinder, and this d1 is also the diameter of sphere, and h is the height of liquid column. This factor 1 plus 2.4 d1 over d2 represents the wall effect correction factor. The measuring cylinder used in the experiment has the finite diameter, due to which the viscous drag force is reduced. Actually, this correction factor arises because the measuring cylinder is not infinitely wide. When the sphere falls through the liquid, the proximity of the cylinder walls restricts the liquid's flow, and this alters the viscous drag force acting on the sphere. In an ideal scenario, the liquid flow around the sphere would be unrestricted, but in a finite cylinder, the walls disturb this flow pattern. This correction factor is necessary. If this correction factor is not applied, the drag force will be underestimated, and this will lead to incorrect value of viscosity. This term 1 plus 1.6 d1 over h represents the end effect correction factor. This correction factor arises because the liquid column has a finite height and the top and bottom boundaries of the liquid affect the sphere's motion. Near these boundaries, the flow of liquid is disturbed, causing the deviations in terminal velocity of the sphere. Without this correction factor, the disturbances near the boundaries would lead to an inaccurate calculations of terminal velocity and subsequently the viscosity. So this correction factor is also necessary. The apparatus required to perform this experiment contains measuring cylinder, liquid that is glycerine, stand with falling ball catheter and leveling screws, emission lasers, receiving photocells, digital temperature meter with temperature sensor, and the digital stopwatch.
This is the complete setup to perform the experiment for the measurement of liquid viscosity by falling sphere method. In this setup, this is the tester unit, this is stand cylinder in which we shall pour the liquid of which we have to measure the viscosity, screw gauge with the help of which we shall measure the diameter of small sphere, vernier caliper with the help of which the internal diameter of this cylinder will be measured. This is the scale with the help of which the depth of liquid column will be measured. These are the small metallic balls. This is the hanging hammer with the help of which this stand will be leveled. This is the temperature sensor. These are the photoelectric gates. This is absorbed steel magnet which will help us to remove the balls from this cylinder. In this stand, this is the bottom plate and these are the leveling screws with the help of which we shall level this bottom plate. These are the photoelectric gates holders in which we shall place the laser diodes and photodiodes. On the top of this stand, this is the falling ball catheter. The purpose of this falling ball catheter is to compel the ball to fall in the straight line inside the cylinder. This is the glycerine whose viscosity is to be found in this experiment. The purpose of this tester unit is to measure the time and the temperature. In this tester unit, this is the timing stopwatch with the help of which we shall measure the time of the falling ball, and with the help of this temperature meter we shall measure the temperature of the liquid. Here we shall connect the temperature sensor on which T sensor is written. This LD1 stands for laser diode 1. Here the first laser diode will be connected. At this place PhD1 which stands for photoelectric diode 1. LD2 here we connect laser diode 2 and here we connect photodiode 2. The first and foremost step of this experiment is to level this stand. In order to level this stand, we shall use this hanging hammer. Let's remove this falling ball catheter from here. Put the hanging hammer at appropriate place. Loose this nut that is fixing this falling ball conduit. You have to adjust the length of this hammer line appropriately to the top of bottom plate. But keep this thing in mind that this hammer should not touch the bottom plate. Adjust these three horizontal screws on the bottom plate such that this tip of hanging hammer aligns the center of the bottom plate round point. At this time, the test frame is basically vertical. After the calibration of verticality of this test stand, you have to connect the photoelectric gates. These are the photodiodes which will be connected at place of PhD1 and PhD2. These are the laser diodes which will be connected at place of LD1 and LD2. Let's connect the first laser diode at its appropriate place and then connect the photodiode at its place. After connecting the laser diode 1 and photodiode 1, With the tester unit, let's place them in top photoelectric gate holders of this instrument test stand. Let's connect the laser diode at one side of this stand and connect the photodiode at other side of this stand. Now connect the second laser diode at its appropriate place and second photodiode at its appropriate place. After connecting the laser diode 2 and photodiode 2 with the tester unit, let's place them in bottom photoelectric gate holders of this test stand. Place the second laser diode on the same side as the first laser diode. Similarly, place the second photodiode. The distance between these photoelectric diodes must be less than the height of the liquid column in this cylinder. Since in this experiment we are going to find the viscosity of glycerine, so we shall fill in this cylinder the glycerine up to 16.3 centimeter. In this way, the height of liquid column will be equal to 16.3 centimeter, which in turn will be equal to 0.163 meter. Let's measure the diameter of this metallic ball with the help of this micrometer screw gauge. Since the horizontal line on main scale exactly coincides with the zero of circular scale, so there is no zero error in this micrometer screw gauge. In order to measure the diameter of this metallic ball, adjust this metallic ball in the anvil and spindle of this micrometer screw gauge. The reading on main scale is 2.5 mm and the 20th division of circular scale coincides with the horizontal line of main scale. So the total reading will be equal to 2.5 plus 20 multiplied by least count, which is 0.01 mm, which in turn will be equal to 2.5 plus 20 multiplied by 0.01, and this will be equal to 2.70 mm. The observed diameter of sphere was 2.7 mm, which in turn will be equal to 0.27 centimeter. When we measured the diameter of sphere second and third time, it also came out to be 0.27 centimeter. Mean diameter of sphere is equal to d1. It will be equal to 0.27 centimeter, and in meters 0.27 multiplied by 10 raised to the power minus 2 meter. After measuring the diameter of the sphere, we have to measure the inner diameter of this cylinder, and it will be measured with the help of this vernier caliper. You are observing that the 0 of the vernier scale and 0 of the main scale coincide with each other, so there is no zero error in this vernier caliper. The inner diameter of this cylinder will be measured with the help of inner jaws of the vernier caliper. Now tight this screw and move it out. The least count of this vernier calipers is 0.05 mm, which in turn will be equal to 0.005 centimeter. The reading on main scale is 6.2 centimeter, and the 10th division of vernier scale exactly coincide with the corresponding division of the main scale. So total reading will be equal to 6.2 plus 10 multiplied by 0.005 centimeter, which will be equal to 6.25 centimeter. The observed inner diameter of cylinder was 6.25 centimeter. Second time, the inner diameter of cylinder came out to be 6.25 centimeter. Mean inner diameter of measuring cylinder equal to D2 equal to 6.25 centimeter, which will be equal to 6.25 multiplied by 10 raised to the power minus 2 meter. Let's turn on the tester unit. Firstly, you have to align the laser diode 1. Align the laser diode 1 in such a way that it exactly points on this string. After aligning the first laser diode, align the second laser diode similarly, that it should also point the string. After this alignment, remove the hanging hammer from this stand. Now align the photodiode 1 and photodiode 2 such that these L1 and L2 indicators goes off. Let's align the first photodiode. Now you are observing that L1 indicator has gone off, which indicates that laser diode 1 and photodiode 1 are properly aligned. After aligning the first photodiode, let's align the second photodiode. Now you are observing that L2 has also gone off, which indicates that laser diode 2 and photodiode 2 are also properly aligned. Now again put the hanging hammer at its appropriate place. After placing the hanging hammer, you are observing that L1 and L2 are glowing, which indicates that this hammer line has properly blocked both the laser beams. Let's measure the distance between both the photoelectric gates. The distance between the photoelectric gates comes out to be 14 cm. Let's note this distance in the observation table. The distance the ball falls at uniform speed equal to L equal to 14 cm, which in turn will be equal to 0.14 meter. Turn the tester unit off and connect the temperature sensor at the appropriate place. Now remove this hanging hammer. Place the glass cylinder at its appropriate place. Turn this tester unit on, and after turning on, adjust this cylinder in such a way that both L1 and L2 indicators goes off. After making all the necessary adjustments, you have to pour the liquid into this cylinder, and after pouring the liquid into this cylinder, you have to adjust the falling ball catheter over here. Let's pour the liquid into the cylinder. While pouring the liquid into the cylinder, you have to keep this thing in your mind that there should be no bubbles in the liquid. Let's adjust the falling ball catheter appropriately over here. Then dip this temperature sensor such that it completely dips into the liquid. Here, one important precaution must be taken into consideration, that this temperature sensor should not block the path of the falling ball. Before performing the experiment, let's note the temperature from this meter, which is 15.3 degrees centigrade. In order to note the time of the falling ball, we have to press the enter button. This time will start when the falling ball will cut the first laser beam, and this time will stop when the falling ball will cut the second laser beam, and the resultant time will be displayed over here. Let's put the steel ball into the falling ball catheter. This stopwatch has not displayed any time because the falling ball has not cut the first laser beam and only it has cut the second laser beam. So let's try another ball. But before trying another ball, press this return button and then press this enter button. Put the steel ball into the falling ball catheter. This time the metal ball has cut both laser beams successfully, and this stopwatch has noted the time, which is 9.2619 seconds. Let's note down this time in the observation table. The time the ball takes to fall the distance L. This time was measured in seconds, and you have observed that this time was 9.2619 seconds. For the second observation, press the return button and then press the enter button. Let's put another ball into the falling ball catheter. In the second observation, the time has came out to be 9.2235. Let's note this time in the observation table. In the second attempt, the time was 9.2235 seconds. In order to take the third observation, press the return button and then press the enter button. While taking the third reading, we are again putting the steel ball on the falling ball catheter and observing the time. In the third observation, the time is 9.2425 seconds. Let's note this time in the observation table. In the third attempt, you have observed that the time was 9.2425 seconds. After performing the experiment, the temperature of glycerine is 15.2 degrees centigrade. Note this temperature. After performing the experiment, remove this temperature sensor and clean it with spirit or any other cleaning agent. Slightly tilt this cylinder so that all the balls in the cylinder attach with this magnet. When all the balls are attached with the magnet, move this magnet up. After removing all the balls from the glycerine, you can clean these balls with the help of spirit or any other cleaning agent.
While performing the experiment, we have noted the observations, and now we are going to perform the calculations to achieve the final results. The density of material of ball which was used in the experiment is 7810 kg per meter cube. The density of liquid chosen in the experiment is 1264 kg per meter cube. As we have used glycerine in this experiment, so this is the density of glycerine at 15.25 degrees centigrade. The acceleration due to gravity has a constant value which is g equal to 9.8 meter per second square. The height of liquid column equal to h equal to 0.163 meter. We have observed the diameter of sphere which was 0.27 multiplied by 10 raised to the power minus 2 meter. And also we have observed the inner diameter of measuring cylinder which was 6.25 multiplied by 10 raised to the power minus 2 meter. The distance the ball falls at uniform speed equal to 0.14 meter. The time the ball takes to fall the distance L. We have measured the time of the falling ball 3 times and then taken the mean, which came out to be 9.2429 seconds. We have already discussed the relation to find the coefficient of viscosity of liquid, which was eta equal to rho b minus rho l g d1 square t divided by 18L into 1 plus 2.4 d1 over d2 into 1 plus 1.6 d1 over h. By substituting all the values into this relation and calculating this with the help of calculator, we get the answer eta equal to 1.514 Newton second per meter square, which is approximately equal to 1.5 Newton second per meter square. So the result is the coefficient of viscosity of glycerine at 15.25 degrees centigrade came out to be 1.5 Newton second per meter square.
For more experiments and lectures, subscribe our channel and click the bell icon.